Welcome to our discussion of the review exercises for Chapter 26. In this chapter, we get a first introduction to the idea of hypothesis testing and look at a couple of specific tests of significance. Our first problem is true-false. The p-value of a test equals its observed significance level. What do you think? The observed significance level it is the same as the p-value. And so this is true. The p-value of the test is the exact probability. The observed significance is the same as the observed, as the p-value, the probability of the result. The alternative hypothesis is another way of explaining the results. It says the difference is due to chance. False, exactly. The alternative hypothesis always says that the difference is not just chance. That's what it says. So, pretty easy. Moving on. One kind of plant has only blue flowers and white flowers. According to a genetic model, the offspring of a certain cross have a 75% chance to be blue and a 25% chance to be white flowering, independently of one another. 200 seeds of such a cross are raised, and 142 turn out to be blue flowering. Are the data consistent with this model? Yes or no, and explain briefly. Well, let's first turn this into a model. What's the first step? Well, the first step is to visualize our box model. So what is this box here? So we have a box where, yep, the ones are blue. We have ones and zeros. The ones are blue. The zeros are our whites. And we know the proportions in the box already. We know that the box, if we could visualize it as, here we go, 3 ones, or we could think of it in terms of our proportions. So this is 75% of the box and tickets in the box, and the white is 25%. How many tickets in the box are there? Well, remember the tickets in this case are, well, I guess we don't know how many tickets from the box. The box is the population, but the data are the point. The important thing to know here is that because we have a 0-1 box, we don't have to actually know the number of tickets in the box because we know the proportions. And we know that our sample is 200 seeds, so it's like 200 draws. So we get 200 draws from this box. And we can, now that we've set up our model, think about our null hypothesis, which says that, oh, wait, I guess, so your book doesn't specify setting up a null hypothesis based on the box model for a counting scenario, but it's still helpful to think about. In the null, in this case, we expect the null to reflect that our observed value is going to be, or observed value in this case as a percentage, equal to the expected value percentage. Because it's still always helpful to think about how you are conceptualizing the null hypothesis, because it's often a framework for whatever test you use. So now we have all of our background information set up, our model here. Let's collect the terms. We know we're going to need the expected value and the observed value. We also are going to need to find out, since we need a standard error, we're going to need a standard deviation. We can move into our analysis. First, as usual, we need, well, we should already know the expected value. What's our expected value here? Oh, I guess we can do this in numbers. It's better. Mathematically, it's easier. So we'll do it that way. And our expected value based on the numbers is 75% times our 200 draws. So the expected value is 150, blue. And what do we observe? Well, we know that 142 turned out to be blue flowering, so that's our observed value. And we're going to need to use our handy standard deviation shortcut for our box. We know by now that when we have a 1, 0 box, that the 1, 0 is going to cancel out. So I'm just going to proceed here down to our the part that matters, the proportion of bigs times the proportion of smalls. And we end up with a standard deviation of 0.43. And we can get our standard error the normal way. We know we can get the normal standard deviation here because we've got 200 in our sample, so it's a reasonably large sample. Standard error is our number of draws times our standard deviation. Which gives us a standard error about 6. So now we can go forth with our z-test, our observed value minus the expected value over the standard error. Observed is 142 minus the expected is 150 over the standard error, which we know is about 6. And our z is 1.3 approximately. Negative 1.3. Thank you. And if you look up a z-value of 1.3, you'll see the corresponding p is about 10%. when looking up this z-value, you want to use remember the table gives you either the mean to z proportion or the proportion beyond the z-score. And this is the proportion we're interested in when we get the p-value. So we go to a z of 1.3. We know that the area beyond z is whatever this proportion is here. In this case, it's 10%. Okay. So are the data consistent with the model? So they're saying does the data reflect the population? Does this difference reflect just chance variation? Remember our rule for our decision rule is when p is less than 5%, it's significant. So in this case, we end up retaining the null. These data are consistent with the model. The observed value %. Remember our decision rule. If our decision rule is that p is less than 0.05, that's significant. P is 10% here, so that's bigger than 5%. So we know that the observed differences are due to chance, which I'm just writing out for your purposes here. But if you're writing this in your result sentence, remember, always write in terms of the variable itself. So this is not my results sentence. I'm just writing this to help translate the model for you. My results sentence would say that the and I'm shortening some of this here, the percentage of blue flowering is, we need our percentage here, the percentage of blue flowering, which would be 142 out of 200. Oops. It's consistent with the expected proportion or percentage of the expected percentage of blue flowers, which was 75%. Comma, remember to report your z statistic. It's negative 1.3, and p is equal to 10%. Oops. I'm just making this more legible. The percentage of blue flowering was 71%. Does that make sense? So the data are consistent with the model, and the difference is marginal. The observed difference is due to chance. A newspaper article says that On average, college freshmen spend 75 hours a week going to parties. One administrator does not believe that these figures apply at her college, which has nearly 3,000 freshmen. She takes a simple random sample of 100 freshmen and interviews them. On average, they report 6.6 hours a week going to parties, and the SD is 9 hours. Is the difference between 6.6 and 7.5 real? I mean, these are both a lot of hours to spend going to parties. Imagine having that kind of time to just waste, right? So of course, our first step is to set up our box model. In this case, what is in the box? Well, in this case, our tickets, it's a little trickier. The number on the ticket, there's one ticket per student. And the ticket has on it the number of hours they reported going to parties. Or, yeah, the number of hours. Okay? And when we draw the tickets from the box, we pick our random sample of 100 freshmen and collect the number of hours for each of them. So there are how many tickets total in this box? Yes, 3,000. The box is the population. We take a sample of 100 freshmen. Those are our draws from the box. We're also given some information. Oh, let's do our null hypothesis too. Well, the null hypothesis, of course, it says that the average is really 7.5. It's 7.5 hours as expected based on this article. We have this expected value based on the article. And our alternative hypothesis says that the average is less than 7.0 hours. Less average the average is less than 7.5 hours. Now you should be already predicting that our next step is to collect our terms so that we can do our analysis and look at our null hypothesis. We know we have 100 draws, so there's sufficient sample size to use the Z distribution here. And we already know the observed value was 6.6 hours. The expected value is what was established in our background information. And we're given the standard deviation, 9 hours. So lots of useful information is given to us. Can you think of other information we're going to need to find in order to do our analysis? Well, there's one more term we're going to need, and that's the standard error. So to get our standard error, we can take the square root of our draws, and multiply it by our standard deviation. Our number of draws is 100 times a standard deviation of 9. And so the standard error for the sample average is 0.09. What? Oh, sorry. I wrote out the wrong standard error here in my paste. We should be taking the standard deviation over the square root of n. I apologize. I know I wrote that wrong earlier too. I normally just start out with the whole z formula as observed minus expected over SD divided by the square root of n. I normally do it all in one step. Sorry. Although we did get the standard error appropriately earlier, we need to use this formula for averages. Our SD is 9 divided by our square root of draws is 100. It'll be 10, which gives us a standard error of 0.9. This quantity is just equal to the standard error. And we can substitute in our values here, 6.6 minus 7.5 over our standard error of 0.9 hours. Thank you, -1. So our z is -1. Remember, in our previous problem, we had a z of 1.3, and that corresponded to a probability of 10%. Well, if we have an even z-score that's closer to the mean, then that's going to have an even bigger proportion outside of it. So now we're at a z-score of -1. And so what's the proportion here? It's going to be about 16%. Thanks, Ashley. Yep, about 16%. Remember, the p-value tells us the probability of getting a score that is at that value or more extreme. So we formulated our null and alternative hypotheses in terms of a box model. Fill in the blanks. The null says that the average of the box is 7.5. The alternative says the average is less than. And is the difference real? What do you think out there? Is this difference real? Or is it this difference due to chance variation? Make a guess. Take a chance. Exactly, Ashley, this is due to chance variation. We know it's due to chance variation because we have a decision rule that is pretty static. It says if P is less than 5%, then it's significant. So we know this is not statistically significant difference. And we know the observed difference is due to chance. That tells us to retain the null. And to write up this sentence, we could say that freshmen at Sample College, we don't have a name for it. The freshmen at the Sample College, and what's their significant or the important statistics to give here? Their mean. Freshmen at the Sample College, mean equals, well, we could wait to put the mean in there. We'll do it, jumping the gun a little here. So we want to say the freshmen at the Sample College had a similar or reported partying for a similar number of hours. So they didn't have the partying. Sorry. And let's see. A similar amount. We could put our mean there, or we could put it here, reported going to parties, after parties. Either spot would be fine. I'm putting it here because that's just where I thought of it. Oftentimes when you write sentences, you have to revise them. That's expected. The freshman at the Sample College reported going to parties a similar amount of time, we should put it right there, as expected based on research. And we know the expected value based on research is 7.5 hours, comma, RZ is -1, P equals, we should say P is about 16%. Whoops. So there you have it. In our next problem, we have I.S. Wright and Associates. We did a clinical trial on the effect of anticoagulant therapy for coronary heart disease. Eligible patients who were admitted to participating hospitals on odd days of the month were given the therapy. Eligible patients admitted on even days were the controls. In total, there were 580 patients in the therapy and 442 controls. An observer says, since the odd-even assignment to treatment or control is objective and impartial, it's just as good as tossing a coin. What do you think? Assuming they did it over 30 days. Well, we can test this. You don't have to just wing it. You should always test it if you can. And in this case, we can simply say, look at this and know, okay, with 580 plus our, if we add our two groups together, we know that the total participants are 1,022. And with a coin, the expected number in the control group would be 50% of this. So our expected value is equal to 50%, or in number terms, 511. So, and with a coin model, the expected number in the control group is 500, would be 511, and the standard error would work out to be about 16, which you could work this out. We've just done it a ton of times here for this 0-1 box. So you can see this would be a, sorry to skip a little bit here, but this would of course be a 0-1 box where we assign we could assign either group to the ones. Let's assign controls to be ones. And treatment are zeros. We know their expected proportions in the box would be 50%. And if we work through this, based on our observed value for of 442 participants, or 42.2%. Oh, whoops. Yeah, not quite. So it works out to be 41.3%, or about 40. Let's say it's about 41%. And we can do our analysis here. Our observed was 422 minus our expected value, which would be 511, with a standard error of 16. So this is going to be a very, very small number. Our, well, very big Z, but a small probability, it's negative 5.6. We know that there was practically a fraction of 1% chance at a z-score of 3. So let's think about our z-score on the normal distribution. Well, now we're at negative 5.6. We're way out here, and we know that this is extremely small, so we could say it's approximately 0% for right now. So the chance of getting 442 participants or fewer in the control group is practically 0. It's not just as good as tossing a coin. Oops. Our null, sorry, I forgot to write the null. The null would just be that the I can say it's the same because that's what we're talking about, is statistical sameness or difference. Oops. I have this extremely improbable z-score. So are we going to reject or retain the null? We are going to reject the null here. Because remember, the null says they're the same. Here we have a very improbable result. If our z-score is very improbable, that means the groups are different. So we have to reject. If the z statistic is small, you must reject. You know that. To quit. Anyway, you probably don't know the media joke I'm making. It's probably too dated. Anyway, so the results will lead to us rejecting the null hypothesis. And we could say that, oh, it's okay. Oh, I'm sorry about that. My buddy bear is laying here next to me, and I forgot and set my I put my hand on there. Why is it so fuzzy? Okay. Our sentence would say that the number of controls sampled using the odd even method, and I said the number of controls, so I'm going to report the number here, which was 422. But I'll also report the percentage. You should really always report the percentage when you give a number, generally speaking, because numbers make better sense as percentages. So even though I framed this in terms of numbers, I'm going to put a comma here and say that's 41%. The number of controls sampled using the odd even method was smaller. I'm stating the direction of the difference. It wasn't just different from what was expected, it was smaller than the number of controls expected based on a coin toss model. And the number expected there would have been 511. That's our expected value, 50%. comma, finally, we always end with our z equals negative 5.6. We can say, for our purposes, p is 0%. Two more. A computer is programmed to make 100 draws at random with replacement from the box 0001 and take their sum. It does this 144 times. The average of the sums is 21.13. The program is working fine, or is it? How do we know if it's working fine or not? What should we do here? Well, how could I start to evaluate whether this program is working fine? I should start where we generally start, with the box model. So we know the composition of the box here, and we know they're taking, so here's our box. They're doing 100 draws and summing them, which is a little different than is different from just drawing from the box 144 times. They're taking 144 sets of 100 draws. And the proportional representation of the box is 20% ones and 80% zeros. We know that already. So based on our model, we can construct our null, which would say that the average of the sums, we call these the sample sums, is the same as expected. Where our expected, well, we don't know our expected value yet. We'll find it though. So now you're thinking about, what terms do we need? Well, we're going to need the expected value for the sum, the standard error for the sum, the expected value for the average. And I'm going to shortcut through these for time, so you'll have the answers and you can work through it later, but I'm just going to give you some of these so that we can cut to the chase of making the decision here. We know the expected value for the sums would be 20. The standard error for the sums is 4. So the average of the 144 sums should be around 20. And then the standard error for the average is 0.33. So let's do our analysis with those data. Well, our observed value for the what was it? Oh, for the sums is 21. Uh, 0.13 minus 20 over 0.33, our standard error. Which gives us a Z equal to 3.4. That tells us it's 3.4 standard errors away from the expected value. Given what we already know about the Z distribution and where a score of 3.4 falls, we could look up this exact p-value. But I remember from earlier that a z-score of 3, which is a less extreme score, had a approximate percentage of, what was it, 0.3% of 1%, very small, beyond 3. So this is, again, a fraction of 1%. It's sufficient to say less than 1%. So, given that we have a z of 3.4, is this variation just due to chance variability, or is it something else? What do you think? It is significant. So will we retain or reject the null? No, we're going to reject. Remember, this the null says that the difference is due to chance variation. The null always says the observed difference is due to chance, period. So we reject the null. We just said it. The observed difference is not due to chance. This is significant. That tells us this is not due to chance. You might be thinking, gosh, should I write out all this same stuff when I'm solving these problems? And my answer to you is an enthusiastic yes, absolutely. Because following this process, as I'm laying it out for you, I'm not writing in extra stuff for educational purposes. I'm writing out this in a way that you should follow logically and go ahead and write out all these steps. If it helps, you should remember to, before you decide about your hypothesis, and remember to interpret your significance level. So you've got this decision rule. If it's less than 5%, then if p is less than 5%, then it's significant. remember to tell yourself, well, significant, what does a significant mean? It means it's not due to chance. How does that translate onto it? Okay, so we'll reject the null. And what does that tell us about this computer program? Is the program working fine or something is wrong? Something is wrong. Hallelujah. Because it's not just chance variability. We could write this sentence. I'm going to skip it though because it's a boring sentence and we have another problem here we need to do. Ouch. So, and a whole nother chapter we're doing tonight. Okay. According to the census, the median household income in Atlanta, 1.5 million households, was $52,000 in 1999. In June 2003, a market research organization takes a simple random sample of 700 households in Atlanta, 750 households. 56% of the sample household had incomes over $52,000. Did median household income in Atlanta increase over the period from 1999 to 2003? So they're really just asking us to compare 1999 to 2003. They're not concerned about what happened in between, but rather what happened at these, here we go, these points. So of course our first step is to establish the box model. What does the box look like? Well, the box has one ticket for each household in Atlanta in 2003. Yes, so there's 1.5 million tickets. And what's on the tickets? The real important part here is what's on the tickets in this box? Yes, it's a 0-1 box. Good eye. So our ones are we'll call ones greater than 52,000 and zeros are less than. Okay. The null hypothesis says that the percentage of ones in the box is 50%. How do I know it's 50%? Because according to the census, the median household income in Atlanta was 52,000 in 1999. So that's our expected value, and that's why we're using this cutoff. And we know 50% is below the median and 50% is above the median. And our data are like 750 draws from the box. I could write out the null in terms of the median household income. I could say that the percentage of households with a household income less than $52,000 is 50%. I'm just writing it this way for space. So let's collect some terms here. Oh, formulate the null and alternative hypothesis. Always remember to answer the right questions. So the alternative would say that the number of to keep it in the same terms, the percentage of ones is greater than 50%. Why did I choose greater? Because we're asked if the median household income increased. Did it increase over the period? Okay, so we've got our hypotheses checked. To do our next step, we need to start by collecting the terms we're going to need. We know we're going to need an expected value and an observed value, standard error, and a standard deviation. We already have some of the terms that we need. Our expected value is 50%, right? 56% of the sample households had incomes over, in our sample, had incomes over 52,000. So that's our observed value. We can put these in terms of numbers too. But we can work it like this. So let's do it. We know we need to get our standard deviation. We can use the shortcut where we know this is 1 0, so that's going to fall out of the equation, or we can take our big fraction times our small fraction. In this case, that's just, they're the same, so it's 0.5 times 0.5, and the square root of that. And we get a standard deviation of 0.5. And we can get our standard error by taking the square root of n times our standard deviation, which is appropriate here because these are frequency counts. Important piece here when you're doing the computations like this to remember to use the right standard error. Square root of 750 times our standard deviation of 0.5 lands us with a standard error of about 13.7. And so we need to get, in this case, a standard error for the percentage of ones in the sample because we're using percentages here. Remember, to turn our standard error into a percent, we just take the observed number and divide it by the n, 750. So the standard error for the percentage is 1.83%. Why get the standard error percent? Well, because we're using percentages. So RZ equals observed minus expected over the standard error. The observed is 56. The expected is 50. Over the standard error here of 1.83, which lands us a Z equal to about 3.3. Remembering what we've seen several times today about the normal distribution and scores. Let's pretend that's pretty more normal. What do you think about evaluate the score of 3.3? What is the probability? Approximately. Well, you should remember this because we've had lots of problems today that had a z-score of 3 or at about 3. This is more extreme than 3. Remember that 3 was a fraction of 1%. This is less than 1%. As we talked about earlier, we can just say less than 1% is sufficient. It's a sufficient level of for our class. As you'll see in SPSS, it'll compute the exact probabilities for you sometimes. So yeah, it's technically, it's not 3% of 1%. That was for a z-score of 3. But the point is that if we remember that 3 is already a fraction of 1%, we know that 3.3, a more extreme score, is an even smaller fraction of 1%. And remember the decision rule. If P is less than 5%, that's significant. So is this is significant? Thank you. So what does that mean? Are we going to retain or reject the no? Yes, we will reject. It's clearly in this column. 5% will be way out here. And it would still be the rejection region. So did family income go up? Sorry again, Bear. Yes, family incomes went up. So to describe that in terms of our sample, we could say that I'd still put in this bit according to the census. Household income in Atlanta was higher in 2003. We can we should give a relevant statistic here. Since the way we measured this was in percentage over $52,000, we can just report it like that. 56% over, we should really say 56% of households over 52,000 annual income. And the household income was higher in 2003 than in 1999. And you would report the 1999 data in a similar percentage, or in a similar way, 15%, ... I'm putting in here for space and time. You would fill in the whole rest of that. Z is 3.3. So P is, you can write out less than or use a less than symbol. I'm going to use a less than symbol because I don't have space. Less than 1%. Oops. So there you have it. We know the household, the median family income went up, and we tested it. We could write a different sentence. You could say, according to the census, median household income in Atlanta was higher in 2003 than in 1999. That would be a better sentence, but either one is fine for our purposes. As a point of interest, Stephanie, we never talk about retaining or rejecting the alternative hypothesis. It just doesn't matter. We retain or reject is only and always about the null hypothesis. So we retain or reject the null. Yes, if we retain the null, that means we reject the alternative, but it's never ever talked about like that. So just as a point of interest, and it's less confusing if you just always think about it in terms of the null, even though it takes a little getting used to the null hypothesis. Great job. We looked at lots of problems that show us how to use the hypothesis testing model with the Z distribution here. And I strongly encourage you to, in addition to this, do the extra problems, the even numbered exercises, try these problems on your own, and then compare with what we found today. Make sure you can do this process independently. And as I know you all are, for the most efficient way, studying statistics every day.